All right, let's go ahead and begin. Welcome to today's webinar. We will be walking through an introduction to Azure Databricks. This will be an overview of what is Azure Databricks, how do you use it, and why should you care? I'm Ken Muse. I'm the VP of Professional Services for Wintellect. If you're not familiar with Wintellect, we are a consulting company, as well as we provide on-demand training and managed services. We're a GitHub partner as well as a longtime Microsoft partner. Myself, I'm an ALM DevOps Ranger as well as an Azure MVP, and I'll be leading today's session. If you have heard of Wintellect, it's probably because we've written the books on many of the topics that you might be interested in, and we've won numerous awards and recognition over the years for all of the work we've done with Microsoft and with our partners. So in today's session, we're going to start with an introduction of what is the modern data warehouse. A basic understanding of this is really fundamental to understanding where does Databricks fit into this. We're going to go through a brief history. How did Databricks come to be, and what was the problem it was trying to solve? Then we'll move into what are the core features? What would you be using it for, and what does it provide? And as part of that, we'll give a brief divergence into what are data lakes and delta lakes, because this is a very common topic that comes up anytime we want to discuss Databricks. And then finally, we'll cover a few of the integrations available natively on Azure as part of the overall solution. So to begin with, if you haven't seen it, Microsoft provides a basic diagram in their Azure docs of what is a modern data warehouse. Essentially, it moves through 4 key phases. Ingestion, let's get the data into the system. Storage, we've got to put everything somewhere so that we can work with it. Then any sort of prep and training we want to do. That is, if we're wanting to modify the data to make it viewable or usable, and are we wanting to bring in any machine learning to our process? And then finally, model and serve. We're going to take that data and we're going to start making it available for self-service reporting and for any sort of jobs that need to run with any regularity to provide us insights into the data. These 4 key phases of the process are universal, but the technologies that can be used at each of these different phases really varies, and it's about picking the right technology for the right job. The main one we're going to focus on today is Azure Databricks. And to be clear, while it is shown on the prep and train portion of this diagram, there are times where it may make sense for it to be part of other processes, including ingestion or modeling. The actual use case and when you'd use it for handling some of the other tasks that Synapse or SQL Server or other traditional tools might handle really vary. And hopefully as part of this session, you'll get some understanding of what is the problem it was meant to solve and how does that play into this discussion. So I want to be careful to say it's not a one-size-fits-all approach. It is not the solution to every problem. And oftentimes the real solution is a mix of one or more technologies. As one of my colleagues likes to say, it's about the polyglot approach. So at a high level, what is Azure Databricks? It is really a managed Spark instance with native Azure service integrations. Now, we'll come back in a minute and really discuss what is Spark and what does that part mean. But essentially, it is a next generation or an enhancement on top of Spark that's built in direct collaboration between Microsoft and a team that includes the founders of the Spark project. So as a result of that, Microsoft considers this a first-party solution and part of Azure. That is, they will support it and they will be the group you engage with any issues. And those issues may pass through behind the scenes all the way to the underlying Databricks team. And when we say it's managed, we mean that it's a set of auto-scaling clusters and pools that are integrated with Azure AD Security that provides an end-to-end solution for you to be able to interact with Spark without the overhead of having to figure out how to manage and maintain a cluster of servers. Databricks adds to Spark several performance and feature improvements, and we'll see that in a minute. But one of the newest is that the engine that powers the Delta Lake has been rewritten in C++, so it's about 20 times faster than the open source implementation just because of the code base. But with other enhancements they've made, other improvement gains that are in there, the overall system itself is easily more than 10 times faster than a vanilla Spark cluster. And in some cases, that number can go up substantially higher than that. So Spark is clearly a very key part of this discussion. So how did we get to Spark? What is it and what does it do? And really, if you're on this call, why should you even care when you've got databases and other technologies available? The modern big data platforms really started to take off with the rise of white papers detailing Google's MapReduce algorithm. This algorithm allowed commodity systems to be scaled up and used to process massive volumes of data with nearly instantaneous results. Prior to this, a lot of the common approaches revolved around having massive computer systems that really had to do all the work themselves, had lots of redundancy, had hundreds of cores. And yet with the original Google systems, they could do the same work with a handful of desktops effectively. That algorithm, once published and detailed, became the basis of the Apache Hadoop project. And this gave us a way of bundling together a number of features, including a resilient file system that could be highly distributed and guarantee that the data doesn't get lost, while at the same time allowing us to build on top of that framework to do robust querying. Now, managing these kind of systems at scale and treating all of the components as resources, compute, memory, disk, versus treating it as actual computers with actual disks where we have to know all the intricate details, was really the theme behind a college project that became part of Apache Mesos. And this project wanted to really abstract all that away and say, how do we just treat all of this as resources that may need to scale up on demand? And then how do we build on that framework? The same team decided an obvious use case for building on that framework would be a newer, more modernized, distributed data querying system that solves some of the problems that they had encountered in working with Hadoop and the related tool sets. This college project was contributed to Apache as well. And so in addition to Mesos becoming an Apache project, Spark came to Apache and rapidly hit its 1.0 mark, becoming one of the most active projects they had. This same team decided to commercialize their endeavors as well. And so the commercial side of this became Databricks. And their commercial offering in the cloud launched just a year after the 1.0 release of the open source. And over that time, they've since innovated, bringing to bear things like Delta Lake and other technology advances that have really become part of the modern data warehouse concept. And you'll see some of these same technologies appear now today in Synapse Analytics, in standalone Spark, and as part of other products. So Spark was designed out of the gate to be highly scalable and to solve a number of problems that came with MapReduce. So what is MapReduce and what problems did we need to solve that really brought this technology to bear? MapReduce begins with a basic concept. We're going to take in some sort of input, perhaps a file with a couple of lines, each listing a number of colors. And we want to get an output. I'd like a count of how many times each one of those words appears in that file. So to do this, it begins going through a process that allows us to distribute the work and then pull together a final answer. And so we take the input and we begin with splitting it. That is, we want to distribute the work across multiple systems. And so we begin by just simply, let's take a line, each line, and each of those becomes a boundary that we could now work on. Those different lines could each be sent to separate servers. And so they're going to be written out to a file system, stored and made available for us to then do a process called mapping. With mapping, we're going to have a node in the system read that piece of work and do a basic job. It's going to begin cataloging all of those items and a count associated with them. So it's going to start and say, okay, I've got one of red, one of blue, one of green from this node, and the other node's going to do similar. It's going to count what does it have. And so now we've got two nodes that each know the count of the individual words, and we've got to start bringing them all those back together. This process is called shuffling. With shuffling, the system's now going to group similar pieces close together, an effort that we will sometimes call partitioning. And it's going to distribute them such that the nodes can find and load that data and that related data significantly faster. In this particular example, you can see that with the groupings, we could easily split this now into 3 nodes that could each process a portion of the load. One doing red, one doing blue, one doing everything else. So now those nodes, having access to all of that shuffle data, will load that data and perform reduce. It'll group everything together, aggregate it, and give us back the final numbers, which can then be output as the end result. Now, it seems like a lot of steps, but essentially what's happening is we're making a trade-off here. By trading off a lot of storage and data being organized in different ways, we can operate with lots of small CPUs rather than having to have one big CPU and one big set of disks run through everything. This enables a lot of commodity hardware to be thrown at a problem and get an answer back quickly, because each individual computer only has to work on a tiny part of the task, with the last system and the first system, the split and the reduce, really being responsible for breaking up the job and then pulling it back together. The downside to this is you may have noticed that each of these steps requires something to be persisted. We're going to be writing things to a distributed disk system. It's going to replicate to make sure we don't lose any data. And then it's available for the other nodes to then read back from disk. Consequently, compute is generally not the bottleneck in these types of designs. Many times, disk I/O rapidly becomes the bottleneck because the disks can only process so much at once. As a result, we ended up with some basic fundamental issues here. The overall system tended to be more optimized for batch. Let's work on a lot of data at one time, as opposed to being able to handle small amounts of incoming data. Every intermediate step needed to go to disk and be replicated, and that created lots of I/O. And with all that I/O, we're losing some of the benefits we got by distributing the system. And then the overall system was not designed to be interactive. If you've worked with SQL Server or other classic database architectures, you're very used to just simply on a command line or through a GUI tool, you create a query, execute the query, and you get a result very quickly. MapReduce wasn't really designed for that. The original architecture was highly programmatic and focused a lot on Java-based jobs. And while tools were built on top of this to make it easier to convert the SQL into those Java-based jobs and then present the results, it wasn't designed from the beginning to be highly interactive, which means we can't get knowledge from it quite as quickly. And that was really the set of problems Spark decided to try to solve. They wanted to make a system that brought everything into memory And then by having as much as possible in memory, the bottleneck goes back to the speed of accessing the memory and the CPU for many of the common tasks. Because of the nature of the original system, they also wanted to start with an overall framework that wasn't just scalable, but was also able to support lots of different languages out of the gate. And so whether we prefer R, Python, Scala, SQL, everything was built up to be extensible, to support multiple languages and features through an abstraction layer. The data frame API, which gives us a way that across all of these systems, the data just looks the same to us. And so I can pull in JSON files, turn them into data frames, make them look like a table that SQL can then query. And I can pick my language. And by having this common set of APIs and this common way of referencing data, we can now talk to any kind of data source we need to. Plus, we can build things on top of it that take advantage of the abstractions so that we can do advanced SQL querying through Spark SQL, real-time analytics with streaming so that as data comes in, it just looks like another table that we're interacting with, as opposed to being a special case. MLlib, machine learning. Take advantage of this framework to be able to do distributed machine learning at scale and pull together the results interactively. And if you have to deal with relationships, trying to identify correlations, networks of activities or related concepts, well, then we're going to start talking about how do you do graph-based programming. And natively, Spark supports that through GraphX, which gives us an entire set of APIs specifically enabling us to treat the data as a graph. Now, I'd be a bit remiss if I didn't mention that the Spark implementation provided by Microsoft on Azure, not Databricks itself, adds one more language into the mix, which is .NET. And those extensions are open source and available, making it possible to use those with Spark and with Databricks with minimal additional effort. So Spark brings those data sets from disk into memory anytime it can to improve performance. And by doing this and having these standardized approaches, it gives us a number of various workflows we can support beyond just the original batch. So we can take advantage of this to then be able to have highly optimized workflows operating largely in memory at high scale. And this gives us the ability to really pull apart data rapidly and get back a response. So it's an evolution of where we were. Under the covers, it's made up of a node, a computer instance called the driver that manages splitting apart all of the tasks, delegating it out to individual workers, and then pulling all of those results back together. It does this through an API and through a relationship with the cluster manager, which is responsible for scaling up, scaling down, distributing the work, and making sure that if a worker goes down, the work gets redistributed. The workers themselves are responsible for both executing the tasks and keeping caches of some data in memory to enable it to be used more quickly. And because each of them have access to the underlying data sources, each one can pull any of the data at any time to do its job, which gives the cluster manager a lot of freedom in delegating the tasks. As you can imagine, setting up all of these components could be a lot of work if you do it yourself. That's a lot of computers to configure, to keep up to date, to manage, to maintain. And this is where Databricks finally comes into the picture. Databricks wrappers Spark with a management solution that completely takes away your need to manage and maintain all of those servers and instances. Instead, you simply say what version of the platform you need and what are the compute and memory resources, what is the SKU of VM you need, And Databricks will manage that, dynamically allocating additional instances and provisioning Databricks, taking away the burden of managing the individual worker and management nodes. In addition, it brings some new features into Spark. The concepts of workspaces, of a unified I/O, of jobs that are natively integrated through notebooks and jars, and we'll dive into these features in a second, and connectivity to most of the other Azure services. And by wrapping all of this up in a nice lightweight experience, it frees us up to focus on the job at hand instead of on the management and maintenance of clusters. So Azure Databricks brings to the table an API for interacting with it, a unified data management surface, including the Databricks file system, which makes all of the different remote systems appear to be just simple local files. Tables and Metastore. Well, we may want to bless those sets of files and folders into being seen as a set of tables so that we can interact through simple SQL queries, or so that we can expose those as SQL objects to the outside world. We get Workspaces, which gives us dashboards, notebooks, libraries. We get the managed computation cluster, and we get the integrated authentication authorization, as well as scheduled jobs. And walking through these, we kind of start with Workspaces because this is the core area we're going to be in. Workspaces take all of the Spark environment and also give us an environment where we can pull together our notebooks, libraries, dashboards of actionable information by team or by individual. We can organize it into folders, and we can easily collaborate and share working together on this information. And when I say collaborate, I don't just mean that the files are available to everyone and that we can all see them and act on them. I mean that we can also have multiple people working on the same notebooks at the exact same time, seeing each other's changes in real time. All of this can be integrated into a workflow that includes Get, which also means we can get some source control. And I'll come back to some of that in a moment. We also have jobs. The ability to create and execute tasks. And these various tasks will be run either manually when we trigger it or on a regular recurring schedule, set up either as a set of interactive fields like a calendar or through standard cron notation. And these jobs can be jar files, they can be notebooks, they can be Python scripts we want to run. The real common connector here is it's something we want to run either in response to an act, a trigger, or with some sort of regular recurrence. Now, I've mentioned notebooks a few times, and if you're not familiar with that, essentially it's a collaborative space for us to create scripts, SQL or code, to interactively explore the data. It gives us a way to quickly create queries, to create interactions, and to see the results in near real time. It supports visualization of the data, including creating charts and graphs, tabular views. It also supports real-time collaboration, as I mentioned. We could have 2 or 3 people in there editing this, fine-tuning it, and bringing their solutions together, all with fully integrated source control. And of course, libraries. If we're going to be doing a lot with languages and programming, be it through Scala, Java, Python, we're going to need the ability to pull these libraries in so that we're not reinventing the wheel. Others have invented systems or code bases which allow us to perform many of our common tasks. And so we want to take advantage of those. We want to be able to pull in libraries that save us time, and we don't want to have to manage how they're distributed onto the various servers so our code works. Because with any script, if I want to use a library, that library has to be running or has to be available wherever my code runs. By having this concept of libraries, we can make sure that every member of our cluster has this code base readily available, and we can take advantage of this third-party code at any time in our notebooks or in compiled code. While I will be addressing most questions at the end, there is one that I do think is very relevant to clarify. Spark works as both an on-premises and a cloud-hosted solution. It's built up on infrastructure, which may include clusters of computer nodes, or it may be managed, such as what we see with Synapse Analytics, where the clusters may be provisioned and managed by a third party. Databricks is a cloud-based solution in which the entire Spark environment and all of these additional features I just mentioned are provisioned and managed for us so that we can focus on creating these interactive Spark notebooks or executing Spark tasks without having to dive into the management and maintenance of those systems on the cloud. There is not an on-premises version of Databricks. Every cloud provider has their own version, their own flavor of Databricks with specific optimizations for each cloud provider, all of which is generally hidden under the covers for you as part of the underlying system. What that means is that when you interact with the Databricks file system, you really don't care anymore what that file system represents behind the scenes. Is it a data lake? Is it blob storage? Is it Kafka? The idea is that as much as possible, we want to abstract that away and let you focus on the work you have at hand. If you're doing your own homegrown Spark, that layer of abstraction really becomes a problem that you have to solve, as does the management of the cluster. And so when we talk about Azure Databricks, we're talking about that fully managed solution and all the features it provides to support you in those endeavors. One of those key integrations, one of the key features is the data lake. A data lake is really a centralized repository for data storage. And while it's not going to store a database file there, such as your SQL Server environments, it will store structured, semi-structured, unstructured data, even binary content, to allow you to process it at scale. Azure Data Lake storage provides you with about a terabyte per second of bandwidth out of the box. It provides you with large amounts of resiliency, and it has a system called namespaces, which essentially are fully blessed distributed folders. They give you a guarantee that related content will be closely situated and available, meaning that things which have been partitioned into folders can actually be queried using that structure without having to examine the entire system. This is a pretty big difference from Azure Blob Storage. The basic Azure Blob Storage, while it appears to have folders, the folders themselves are actually nothing more than part of a very long file name that happens to have slashes in it. The modern tools have made that appear like folders, but if I wanted to query everything that's in some child folder, I would actually have to query every file in the underlying blob storage to get its full name, parse out the folders to identify which file names have that particular folder path. Azure Data Lake is different. Because it has namespaces, it can actually have true folders. And therefore, when I say give me everything in a folder called year equals 2020, I am now narrowed to just getting back a list of files or folders that are in that particular folder without having to iterate the entire lake. This gives me scale on querying the resources. And while this all may sound somewhat complicated, at the end of the day, a data lake is nothing more than files and folders. It really is that simple. And so when Databricks interacts with this system, it's really just reading files and folders that are managed and maintained for us at scale and making it look like local files and folders to the system. These files and folders, when we're talking Databricks or some of these other big data systems, are optimized and organized, going from the raw data in whatever format it's in to a more structured format that is better optimized for querying and analysis. While partitions themselves are largely organized around folders, the file format is then something that's optimized within those folders to enable querying at high scale and with little contention. One of the main ones you will encounter in working with Databricks is the Parquet format. Parquet files are a binary format representing columnar data that are highly compressed and very much optimized for reading column stored data sets. While there are other formats that are better optimized for things like row-based data, as we move through a Databricks system, ideally being a big data system, we're going to start looking for how can we build up those columnar models to enable data warehousing and our ability to efficiently analyze at scale. To that end, Parquet files support something else, schema, the ability to define the type of data that's stored within it and to be able to query on it against those columns and rows. It also has a concept called splittable metadata. The idea of that being that as we move to scale, we may want to be able to pull apart the Parquet file and load parts of it across multiple nodes. And that way each node can read the individual parts. Parquet files have a footer that tells it how to find all of the different breakpoints and to provide it a summary of what is actually in each of those chunks. This makes it very, very efficient for a system such as Databricks to be able to load Parquet files across multiple nodes concurrently, loading either entire files or chunks from the files, and caching that metadata so that it knows how to get the rest of the data if and when it needs it. With Databricks, this model had to be evolved because coming at it from a SQL world, coming at it from a more traditional world, the eventual consistency model, the levels of trust that go into optimistically looking at these data models start to create issues at scale. So what the Databricks team has done is they created a format called Delta. And it takes advantage of the features of Parquet, along with some additional Parquet and JSON files for tracking changes, to give us ACID transaction support in the data lake. What this means is that Databricks can upsert, insert, merge data into these tables with full ACID support. The tables themselves, because of the way this is laid out, can be petabyte scale. And because of the nature of the way all this looks through the APIs, batch and streaming appear to just be the same thing, a table structure, rows. Delta also adds in two big enhancements to the overall Parquet approach, beyond just ACID. First, schema enforcement. We can actually choose to say that the schema is immutable and that we need to have special handling if schema is changing. This is an area where Delta continues to be enhanced and more features keep emerging to support their eventual goal of having more complex validation than just simply what's the column type. The other big part to this is time travel, data versioning. The idea that I may need to know, what did my data look like 2 weeks ago at this time? And what has happened in the 2 weeks since then? If that sounds like change data capture, it is in many ways a CDC approach. And the level of change that we're keeping and capturing is configurable and is actually managed as part of those overall transaction logs that are being committed with each and every new insert or update. The Delta project itself is an open source project. This was essential to make sure that the community would really buy into using the overall Delta format. So it's been contributed back to the community, and it is available with Spark. It's constantly updating to bring new features to the table. That said, Delta with Databricks is slightly enhanced. And by slightly, I mean that they've made some very big improvements to key characteristics that help with performance. First, the new Photon engine is a rewrite of the code in C++. This rewrite gives it significantly better scale by allowing them to actually create pipelines at the individual low-level core and threading levels in the CPU. By being able to take advantage of those kinds of optimizations where they're actually interacting with the chip at that low of a level, they've been able to realize significant performance improvements. For example, rather than just simply creating one value if a certain case exists, and another value if another one does, meaning two different pipelines, they may actually optimize it by running both at the same time on the CPU, and then just keeping the first one, because the overall time will be perceived as faster. The other big enhancement is a thing called Z order indexing. That is, when they write the Parquet files, there's some additional optimizations done and some additional metrics stored that enable Databricks to very efficiently scan the Delta Lake for where those individual chunks are in the Parquet file that satisfy a given query. This means that it can highly optimize how it's going to load the Parquet files into memory and which parts get loaded to which nodes. Instead of just simply avoiding data that can be skipped through partitioning and partition elimination, this particular enhancement means that even within the Parquet file itself, it can eliminate chunks that don't satisfy the query. And that means less data motion and a more effective access to the data that needs to change. So if we're using Spark, we have a version of Delta, but if we're using Azure Databricks, we get a highly optimized model. And under the cover, this model relies on certain key behaviors of the underlying data lake to ensure those ACID guarantees. This is a big difference from the other implementations of Databricks. Azure Data Lake natively supports the semantics needed to get that level of locking. AWS and some of the other implementations require a service that acts as an intermediary to provide those same guarantees. And so there is that extra layer that's hidden under the covers if you're talking AWS GCP. So that enhancement on Azure Databricks does give it a slight edge in the overall performance because it's able to take advantage of the underlying system. As a developer, the code to you looks exactly the same from the front end because it runs through the Databricks file system. The file system, and I'll show you this in a minute, simply mounts remote systems, blob storage, data lake, as if it was a local file system. It looks like local files and folders. Additionally, that act of loading it and the acts of using it can result in that data being cached into memory. And so while it appears you're reading and writing folders, you may also be reading and writing memory locations that then persist to highly distributed folders. Committing to these local folders results in it committing back to the data lake or the underlying blob storage. And so you get the resiliency and guarantees that come with committing your data into cloud scale storage. Everything automatically persists. But from our perspective, whether it's an insert statement in SQL or a write command in Python and Scala, it's just simply committing data back to the file system, and whether that file system is in memory and passing through back to a data lake is all hidden from us. Again, it's really about the experience of being able to interact with the data to make decisions or process the data, as opposed to focusing on low-level implementation details and creating your own abstractions. Because of this, we can take advantage of something called structured streaming. Structured streaming makes incoming data look like just another table. It's simply rows that are getting a constant set of inserts. And this could be files hitting the data lake, bringing in new data. This could be changes to an underlying Parquet file or Delta table. It could be a Kafka stream or an Azure Event Hub stream. As the data arrives, it'll appear that a new row was added to a virtual table, which means we can join it, we can query it, we can analyze it. We can do aggregations and window operations over it so that we're able to act on the data as it arrives. For example, I could keep running averages. I could look at counting transactions, summarizing data, looking for patterns, and updating other systems based on that. And because it's all abstracted away, I really don't have to worry about the how behind it. And if I commit changes to other records, I don't really have to worry as much about where that data is stored or how. I just simply interact with my data and make the changes I need. And so whether it's real time or batch, Databricks makes it very easy for us to treat all of the data as if it was just simply table operations. To facilitate this, there's a model you're going to hear about a lot with Databricks. And it's not the data lake or the newer Delta Lake, which is the data lake with the Delta files on top, but it's the Medallion architecture. The Medallion architecture simply says that when we get the raw data in, we're going to want to persist that. Raw data has information that only exists at the time we get it, the metadata about when it arrived, any details the system provided or that came with the message. By capturing the raw data, if we ever need it again in the future, we have it persisted in the data lake and we can act on it. If we make a mistake in a calculation, we can see what was the original data to figure out what should the new values be. But raw data itself may not be actionable and often requires cleansing to make it usable. We're going to want to filter it, augment it, standardize the way it is organized into a more traditional schema that allows us to begin to get some insights and be able to build more robust solutions. And so that creates what they call the silver tier. Moving from bronze to silver could be a stream, could be a batch job, could be a combination. As we move into silver, the data becomes standardized. It may become optimized for doing deeper analysis. So we may have 3 or 4 pivots of the data into different formats, each optimized to pull out specific things we need at very high speeds across the cluster. But ultimately, once we get the data in a way that we can now begin to pull together actionable results, we're going to want to stage that data for additional consumption, either directly through the exposed SQL or pushing it into a more traditional data warehouse so that it can take advantage of all of the features that are native to tools like Azure SQL Server Hyperscale, or if it needs some additional analytics, perhaps a Synapse analytics system, the former Azure SQL Data Warehouse. There's lots of different ways we could look at that. We could also push it directly to an Azure Analysis Services, or a Power BI. The great thing about being able to mix code and SQL is we get to decide where we draw those lines. But essentially, gold represents the data in that end state, in that clean, queryable, well-designed model that'll support the reports we need. If at any time gold needs to be updated, we can pull new data or updates from silver. If silver needs to be corrected, well, we've got the bronze data to help us with that. And again, whether these jobs are batch or near real-time streaming, it all looks like tables under the covers. And so we can create these complex pipelines that carry the raw data directly into a reporting system with very low latency. Generally, each of these systems is optimized for that use case. And so with Databricks, you will often find that while raw may be JSON or the native incoming format, Avro if you're using event hubs, Silver will often be a Delta Lake. It'll be using the Delta file format to take advantage of all the benefits of that, partitioned to make sure that it really helps you service the data rapidly. Moving to the gold tier, that data may be Delta if we're going to be querying directly from Databricks or from a Delta-enabled Spark cluster, such as using Delta jar files and supporting libraries through any third-party system. Or we may decide we want to output the gold as Parquet files because we're going to use a system that understands Parquet natively, such as Synapse Analytics. Or perhaps we want to output it as CSV because the system it's going into only can handle tabular data through the CSV format natively. And so gold is optimized specifically for that load process and the end system that's going to use it, while silver is optimized for being able to analyze the data and be able to receive it into a format we can use to build the gold as quickly as possible. And before I show you a couple of these pieces, I want to finish this with some of the integrations we have available. Natively, we can interact with Azure Data Factory. We can invoke the notebooks or jobs directly from ADF. We can take advantage of Azure Functions to trigger actions and to invoke the REST APIs that Databricks makes available. So we can respond in near real time through Azure Functions, invoking something in Databricks to trigger a process. We can integrate directly with Event Hub, pulling data in as streams, or relying on the fact that Event Hub has a model where it can directly persist the files in Avro file format to the file system, meaning that we can completely abstract the way we're handling it. If you use this Event Hub integration, it's near real time, while the file system-based one has a minimum 2-minute latency because of how it batches together messages in the same time frame. You will notice that the current version of the libraries that support that do target specific versions of the Databricks runtime and specific versions of Spark. Additionally, the Cosmos DB integration, which currently targets Spark 2.4. So if you're going to interact with Databricks, it would have to be an older version. But these libraries are being continuously updated to provide the latest features, so that should change in the coming near term. And Azure SQL Database and Synapse Analytics. If we want to interact with those environments, there's a connector available, and all of these connectors are open source, which allows us to directly interact to update or query tables in these systems, allowing us to interactively work with the overall system. So I'm now going to quickly switch over to showing a little bit of this in the Azure Portal to help you get oriented. To create a Databricks environment, simply click Add on a resource group, and we're going to create a new Databricks cluster. Now, you would think typing Databricks in the search would bring up the option. Unfortunately, out of the box, it doesn't. So, expert tip, if you type Azure Databricks, that will bring it up. So if you type Azure Databricks, you'll get the option to create the cluster. And then you'll just follow the wizard to create your environment. Key tip here is to make sure that when you create it, the region should match the region your data is stored in. If it doesn't, you're going to rack up some rather hefty transfer fees because you pay anytime data leaves one Azure region and moves to another. So making sure the region matches is a key way to avoid high costs. You're going to pick a pricing tier. If you're getting started, take advantage of the 14-day trial. You just pay for the VMs and the underlying data lake. You don't have to pay for the DBUs, which is the pricing model, the licensing fee for Databricks that sits on top of the VMs. The choices we have beyond that are standard, which is the core features and functionality, and premium, which adds a richer set of role-based access controls, pass-through identity, so your identity goes with you, and the enhanced Delta engine called Photon. We get a number of networking options, including, do we want to eliminate a public IP? Do we want to limit which VNet it's in? And we have the ability, through some new functionality, to be able to double encrypt the data. Beyond the encryption at rest that the data lake provides us inherently, we can also add an additional layer of encryption on it. So even having access to the data lake is not enough to be able to get the content out of the files. Once you go through these steps, the environment will be provisioned. It generally takes under 10 minutes. And you're going to get a new service available that when you click on it, gives you the ability to launch your workspace. You'll notice that the integration with Azure Active Directory means that you pass through directly into the workspace using your credential. If you're paying for premium, then as you start to mount file systems and data, your credential carries through. As a first step, you'll end up creating a new cluster. Clusters are simply groupings of servers. If I create a new cluster, which I will click Create Cluster, I can give it a name. I can pick the type of task. Is it a high concurrency task that is lots of concurrent reads and writes? Is it a standard node? I'm going to be doing processing, but it's not going to have a lot of concurrency issues. Or the ultimate developer mode, single node. Single node lets you work with a lower cost setup. The trade-off being that your tasks aren't distributed and you won't be able to fine-tune the distributed nature until you have multiple nodes. I can pick a specific runtime. Anything with ML is optimized for machine learning. And the different runtimes correspond to different versions of Spark and Scala, as well as some feature sets for Azure. Finally, I can choose a number of options such as, do I want to have credential pass-through? What size of worker do I want? What's the minimum and maximum? Do I want to use lower cost spot instances? Should it automatically scale up and down depending on how I'm using it and terminate when nothing's being used? Or do I want to fully customize it from a Docker image? One feature to be aware of here is pools. Pools give us the ability to create groups of servers that are hot and available. In this case, I've got 3 instances that you can see are idle and ready for me to use for some Spark queries that I'm going to show you. By having these hot available, they provision more rapidly. Instead of typically taking 5 minutes to 10 minutes to stand up, they can be ready in just a couple of minutes to use. In addition, pools provide an extra addition if you've got a lot of interaction going on, or you're needing to dynamically move between workload sizes. Whenever instances are returned to the pool, that is, they're not needed and we've scaled down the individual cluster. If we're using pools, anything idle in the pool does not charge DBUs. It charges the base VM price only. That means I can cut my costs. So if I need 8 nodes on hot standby, I can be paying for 8 VMs instead of 8 Databricks VMs. When all 8 are in use, well, then I'm paying for the VMs plus the Databricks license for those on top of it. And when it scales back down, they return to the pool and I stop paying the extra fee. Within Databricks, through either Workspaces, which allow the concurrent work, or repos, which are a newer feature designed to allow us to manage notebooks at scale, separating production, test, and other environments. I can choose to create environments that are code either as Scala, Python, R, or as SQL. If you're first starting out, you'll find in the docs that it walks you through how do I mount my data lake or my storage. This is going to be your first step because you're going to provide it the credentials or tell it that it's using pass-through. And you're then going to call dbutils fsmount to tell it that I want to take a file system that's remote and I'm going to mount it to a specific location on the file system. Once it's mounted, it becomes just a local file system called mount, in this case, mount site logs that I can interact with. If I'm using blob storage, the main thing that changes, you'll notice, is the actual type of connection. Once I have data mounted, I can then begin using Scala, Python, R to analyze and process the data, to convert it to different formats, and to potentially persist it in a way that I can then query it. And so with that, I then have the ability to do a full SQL query where I can do simple things like executing a count statement. Now it's noticed that that cluster has timed out, so it's reprovisioning one, and it's going to run that statement. When it does so, it's going to cache all that data so that if any more statements have to run that are similar or related, it's going to run in substantially less time because key data is all in memory. You'll notice that I can create simple queries, execute them, and get results. I also have the ability to create jobs that will execute these kind of queries on the fly or in response to a schedule in the background. And I have the ability to say, I want to change the visualization between a table and one of multiple different formats for presentation. Because all this is HTML, I can capture it and save it off. I can choose to hide certain values. I can add additional titles for context. And I can even capture these components to create dashboards within Databricks to help my team. You can see here that our query is now finished. The environment came online. Took 26 seconds to parse through 200 million rows. Now, because this is all in memory, if I execute it again, you'll see it submits it, and it took it only 2 seconds because now key aspects of this data are in memory, and so it no longer needs the file system to answer this query. This is the real-time interaction, and it can automatically scale up and down across numerous nodes to support this. Now, obviously, there's a lot more to be said about Databricks, and this is just an introduction to get you started. We're always glad to connect with any of you offline to provide you more insights and more details. And as a reminder, this video will be posted and made available for you to review at a later time. So definitely feel free to reach out and connect with us with any questions. I'll be around for just a little longer. If there are any questions from anyone in the group, I'd be glad to try to answer them. All right, I'm not seeing any new questions. So if you have anything, please let us know. Otherwise, we look forward to connecting with any of you that may have questions after this. And we hope you found this session a helpful introduction to getting to know Azure Databricks. We do have a couple of questions now. The first one, how would you compare the use case between Databricks and Synapse? So Azure Databricks provides us the ability to parse the data at scale. Some of the newer features in Synapse, including its Spark clusters, do provide similar functionality. The big things that are different, Databricks has access to the enhanced version of the Delta format, so it can actually interact with the files in that format substantially faster than the Parquet format that Spark under Synapse or even the Azure SQL serverless pools can currently achieve today. Microsoft's continuing to enhance that and work on it, including adding their own additional indexing structure on top of it. But at the moment, it is faster on Databricks. Another big use case with Databricks is that because of that, it can satisfy some additional real-time ingestion needs by being able to run jobs. These jobs can be scheduled jobs, but it may also be that you're running long-term streaming jobs. And so while these tasks are running, your data is coming in, being processed, and moving through the Medallion architecture. Today, that isn't available unless you add in the Azure Data Factory component, which takes advantage of some of the same technology to provide some of the same features and functionality. Now, at the same time, whether it's Synapse or SQL Server, traditional databases have the concept of indexes. You can index multiple columns, enabling it to do a different kind of elimination to get to the data you care about. That means that if you're interacting with a SQL Server or a Synapse environment, I can hit that environment and take advantage of indexes to be able to get through the data very quickly. Unfortunately, you'll notice that the Delta format is really limited to partitioning logic and some metadata inside that helps optimize the queries within that. But that's very different from traditional indexing. So there's a number of features and functionalities that are a bit different. And we could summarize some of that to say that there's a number of use cases for ingesting data or doing ML on data where Databricks may be significantly better suited. It is not every case by any means. On the other side of that, if we're wanting to do lots of set-based aggregation, more traditional SQL that relies on indexes, models that need multiple sets of indexes, and we don't want to create different tables with pivots of the data, or we can't rely just on Parquet, on partitioning and the built-in metadata, well, then a SQL solution may be a better fit. And if your flavor of SQL that you're used to working with is T-SQL, and that's your comfort zone, the SQL is closer to ANSI SQL with some Spark enhancements. And so T-SQL, that's a Synapse-only thing. So I hope that gives some idea of how those systems compare at a high level and where some of the advantages come in for Databricks versus Synapse. At the end of the day, it really depends heavily on the job you're trying to do and the task you're trying to accomplish. And if the parameters of that task change, one may be better suited than the other. And this is an area that Microsoft is investing heavily in. So I do expect the two products to only become more competitive over time. So Joel, Demu, I hope that, and Lucia, I hope that helps explain those differences. Any other questions? All right. I'll give it just another minute in case we have any last minute questions. All right. Well, thank you all very much for attending. Very much appreciate having you on to all joining us today. Again, if you have any questions afterwards, please feel free to reach out either via Twitter or to consulting@winelike.com. We'll be glad to help you get started on your journey. And we look forward to seeing you again in the next webinar. Thanks a lot.